Okay, picking up after break, we're going to go along to the next section here. So we've looked at how to initialize and define buffers, but now we really want to be able to do something with them. I think the ones that we're going to find most useful are real number buffers, because we can store pieces of data in them and then retrieve and optionally sort that data later on. So, when we're doing real number buffers, this part becomes really important to accessing real number buffer data. A buffer can have many reals in each record, but the read and write commands use a single variable. The variables specified on the left side of the equation is the first of a sequence of consecutively defined variables. For example, fmt4 b1 underscore x, b1 underscore y, b1 underscore z. Another way to define them consecutively is to not use the formatting, it's to use the normal initialization. So here we would have b1 underscore x, b1 underscore y, b1 underscore z. In either of the above examples, the MP language will treat all variables as an implied array for functions that require more than one element. Since there is more than one way to declare a variable in the post writer might accidentally disturb this ordered list. Be careful not to format one of the variables and later try to define it as a consecutive variable in the initialization area. Once a variable has been defined, it cannot be redefined. In this example here, you'll notice that in this 3 consecutive variables, they're using b1x, b1y, b1z. Unfortunately, b1y was already formatted up above. So if you reference a set of 3 variables using b1x, it's going to use b1x, b1z, and rc2 as the 3 variables in the list, because it will ignore this definition here for b1 underscore y, because it's already been defined up above. So you got to be really careful of that. You can use either a variable name for the buffer number and record number, or a constant. However, you would usually use the variable name, because every time you read from or write to a buffer, the variable that represents the record number is automatically incremented by 1. The exceptions to this rule are when you read record 0, or when you have defined buffer no index set to 1. In these cases, the system will not increment the variable. The variable that represents the buffer number and record number are not predefined, so you must define them in the post customization file. Okay, we've looked at this example just a little bit, where with the strings we did a write counter and a read counter. Okay. We're going to go through and do our own numeric variable example. But I also think we're going to look at some examples of existing buffers in an existing post, so you can get an idea of kind of how powerful they can be. So for this example, we're going to go look in shared mkmx, lathe, posts. And we're going to take a look at the generic Fanuc 4x MT lathe post. By the way, this has a similar structure to all of the 4x lathe posts, so the generic Haas SL, the ST, the Haas DS 30 SSY, the Morisigi MLX 2500 4x, a bunch of these posts were derived from generic Fanuc 4x MT lathe post. So we'll go ahead and open that up, and I'll search for fbuff. And this post actually has 3 different buffers that are used. Buffer number 1 is a numeric buffer, and you'll notice that it has 29 reels per record. That means that every time we read from or write to buffer number 1, we are reading and writing 29 separate pieces of data. Okay? So I like using this one as an example because it's an example of kind of one of the extreme cases of what you could do here. So what we have going on here, you'll notice that we've got buffer number 1, tool change information. We've got our write counter and our read counter, and our next counter. This is the initial counter for the read buffer 1 into the next record. And then we've got a variable here for size 1 to get the buffer size. Then what you're going to see is something that may look a little confusing. We have current tool information. And if we start at 1 and count down, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. There are 29 variables that are initialized in order, and you'll notice they all start with C1. Then you'll notice, if you count down, and you start here at N1 G code, and we count, and I've done it, so no need to count them all for you out loud, but we get down and there are 29 variables that are also in order, starting with N1. The way that this is set up to work for buffer number 1 is that we are going to write the current tool information for each kind of tool change event. And then we have 2 sets of variables, because when we go to read the values, we are going to read the current tool information from our buffer. That gives us our C1. And then in order to read the next information for what's coming up, all we need to do is use the NC1, which is the next record counter. Read buffer number 1 using this counter, which is already incremented by 1 record ahead, and we're going to load that into the next tool information. Okay? The place that this happens, if we go look for wbuff, there is a post block. Let's see. Are you using the lathe.pst? So Donald's asking a question. We are looking at the generic Fanuc 4x MT lathe post. So this is a generic post that ships with X7. And I don't believe anything special has been done to this post processor. So this one should just be stock out of the box. And the reason that I like to bring it up as an example is because it uses this buffer right out of the box. So P current record, right? Write to the current tool record. PCUR_RECD. If we look at where this gets called, it gets called right here from PWRTT. And so what happens, PWRTT, the tool change post block, gets called during the pre-read process. So during the NCI pre-read, we make a loop through the entire NCI file. And for every tool change event, we call PWRTT $. And based on the value of things like G-code or what the opcode value is, we decide whether or not we want to call some things. This P current record gets called every time no matter what. There's no if condition on there. Okay? So with P current record, we call this. And what you're going to see is that the variables all get set before we write to the buffer. So C1 underscore G-code equals G-code. We run some setup post blocks that calculate some values. And what this does for us is gives us, for example, the calculations that calculate the values of X abs, Y abs, and Z abs. This line of code here uses a piece of vector math called vector equate to copy 3 values starting with X abs into 3 other values starting with C1 underscore XH. So what this line of code does is copies X abs, Y abs, and Z abs to C1 underscore XH, C1 underscore YH, and C1 underscore ZH. So that it's important to understand how this works, because here we're actually setting 3 values. Here we're also doing the same thing. We're using VMAP to set the tool plane origin, and we're going to map the tool plane origin X, Y, and Z components into our machine matrix. And we're going to take those calculated values and we're going to load them into C1 underscore TOX, C1 underscore TOY, and C1 underscore TOZ. So these 2 lines here set 6 different values. So we've set a value here, that's 1. We've set 3, that makes it 4 total. We've set another 3, that's 7. Here we set our 8th value. Here we set our 9th value, this if-else statement. Here we set our 10th, our 11th, our 12th, our 13th with this if-else, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And there may or may not be one in here. X max equals X min. Anyway, this line of code here is where we actually take all of these values and we write them to our buffer. So remember that when we write to a buffer, if we've defined it with 29 values, 29 real numbers per record, we need to set all of those values first. And then when we perform this one line of code, we're writing all 29 of those values at once. So, when it comes, so this is all the writing of the data. Okay. Now we have a block of code called p read current underscore next. P read cur underscore nxt. And that gets called on the call to pmisc real. The reason we call it during the pmisc real post block is because if you look at the NCI, let's do this. Let's post that out, and let's just look at the NCI data. The NCI 1011 line is where we start reading the operation data for the upcoming operation. So this is the miscellaneous reals, this is the miscellaneous integers. And let's go down through our first operation. There's our first operation. You can see that when that operation ends, we get the next 1099, we get a 1051, we get a 1053, and there's the 1011 line. So the 1011 line is output very early in that NCI sequence. And that's why they have keyed off of this. And it says call on miscellaneous reals, okay, if tool table active or tool change does not equal 2, then we're going to process all of this stuff here. Okay, so if tool table active, RC1 equals 1, size 1 equals read buff number 1, we're going to read the 0 record. Okay, and if CC 1013 equals 0, CC positive equals 0. Right? Now it says if RC1 is less than size 1, P, read current next. Okay? So, P, read current next reads the current and the next tool record. One of the things that we don't really have the ability to do. Oh, did I close it out already? I must have closed. No, I didn't close it out. Okay. One of the things that we don't really have the ability to do is read ahead in the NCI file. There are some limited mechanisms in the NCI that will allow you to read ahead to a limited extent. For example, we can enable the get next variable routine, and you can kind of look ahead. But if you end up using a buffer, you've got the ability to scan ahead or behind or do whatever you want, because we can manipulate the record numbers to search forwards or backwards. So for example, one of the things that we have here is this P read current next. So C1 G code equals RBuff 1 RC1. What does this do right here? This single line of code to read the current tool record will load all 29 values from buffer number 1, reading whatever this values this RC1 has for its value. So if RC1 is 1, we're going to read the first line. If RC1 is 10, we're going to read the 10th line from the buffer. But keep in mind, as soon as we complete this action, RC1 gets incremented by 1. Okay, so if this was 9, we're going to read all those values, and once we're done reading all those values in, it's now going to be 10. So now what we do is grab all of our global variable values, cut type, lathe CC, G code CC, y-axis, mil CC. We grab all of these current values from the buffer. So we set C1 cut type, C1 lathe type, C1. So we read all these values, we load them in over here. Then down here, we read the next tool record. N1 G code equals RBuff 1 NC1. NC1 and RC1 are always, the NC1 counter is always one number ahead of RC1. And what that allows you to do is to grab the next tool record. So here, let's say we were reading record 9 up here. We'd be reading record 10 here. If we were reading record 4 here, we'd be reading record 5 here. That's the way that this is set up to operate. So now what we're doing is we're reading one record ahead, and we're placing the values of all 29 variables in the list of 29 variables starting with N1 G code. And this is the kind of confusing thing about what we're doing here, because when we write all this data, we're only using C1G code. We're writing it all in using the PWRTT mechanism. Then when we go to read the current and the next, we're reading all that data from the buffer and we're reading our current values, and then we're using this counter here to read the next values and load them in for us. So what that means is that when we start an operation, we have available to us the values of the C1 variables and the values of the N1 variables so that we can do comparisons. So if I search for if C1 underscore, you're going to see actually, let's search for N1. There are several places in this post that we do comparisons or look ahead to see what the value of the next operation is going to do. So if N1 CC pause, so if the next operation coming up CC pause is turned on, we're going to do all that stuff. And there you'll see that kind of all throughout the post. There are these things where we take the values gotta get out of the current record. Let's go back up to the start. So now I'm searching for C1 underscore. Okay, so here you're going to see these references as I search through where we're comparing the values to the buffered values. Okay, here we're setting, previous XIA equals vector equate C1 X home, Y home, and Z home. So we're setting the previous XIA, YIA, and ZIA values. Here we're outputting lathe canned cycle cutter comp. We're reading the CC pause value from the current tool record. So you're just going to see that kind of throughout the post here, where we're checking these values from either the current or the next tool buffer. So anyway, this was, again, one of the larger examples of where, we are capturing values and we are writing them to a buffer. So I wanted to make sure that we pointed out some actual uses of buffers in our posts as we go through this class. Okay. All right. Let's see here. Just checking something out real quick. Okay. So the next thing that we're going to look at is our own example of a real number buffer. So we'll go ahead and close that out. We're going to use MP-fan again. Okay, so that's our first buffer. And now we're going to think about making our second buffer. Okay, we'll call this buffer 1. Well, down here we're going to do buffer 2. Okay, so this is buffer number 2. We are going to keep the buffer number when we're done, the buffer 2. Now we need to decide how many reels per record we want to capture. Let's do this. Let's capture our tool plane origin for each tool plane that's going to be output. So in that case, we're going to want, actually we'll probably want 4 records, because we're going to want to grab an XYZ value, but we also may want to know something like the operation number, something like that. We don't want to initialize it from an existing file, and it is not a text buffer. It is a real number buffer, so the last 2 values are 0 and 0. So again, it's buffer number 2. We are going to keep it when we are done. We have 4 reels, 4 real numbers per record, so per row. We're not initializing it from an existing, and it is not a string buffer. Okay, so what we're going to do is we're actually going to copy the sbuff name 1. We're going to change it to sbuff name 2. And let's change this to buffer 2, and we're going to make it txt2. Okay, I could just make these txts, right? We could just make them standard text files if we wanted to open them with something else. Because in this case, the buffer name that we've given it kind of indicates which buffer it is. But this is kind of the standard convention. txt1, txt2, txt3. So we'll just stick with that. We always want a variable to be the size counter. And we're always going to want a read counter. So this is going to be RC2 because it's for the buffer number 2. So read counter for buffer 2. We want WC2. Okay, and we've got the write counter for buffer 2. Now we're going to need a list of, we got a question from Donald. Could you use .doc or .pdf? Sure. Yeah, if you wanted to open it up as a setup sheet, you could definitely use .doc. You could use .pdf. You could make it put that extension on there, but it wouldn't actually be formatted in PDF format, so I don't think that would work for you. In the reality, the only thing it outputs is ASCII text, so there's no formatting that we can apply to the data that we're outputting, unfortunately. If you're looking to do something like a setup sheet, the best thing that I have found is to output the data to a text file with space delimiters, because that's how it does it normally anyway, and to read that data into Microsoft Excel using the special text import options and tell it that it's space delimited data. That seems to be because once you get the data into Excel, you can do a lot of stuff to format it. You can import text and graphics, you can arrange stuff, you can apply font sizing and just all those different types of formatting, right and left justified, word wrap, all that stuff you can do with the cells. And unfortunately, you can't do that with an MP buffer file. Might be another class, yeah, absolutely. I could definitely see doing something on that. It would be definitely fun to do because those are the things that I think really extend and enhance the MP language. I mean, buffer files themselves are pretty powerful. I think you guys will see that by the end of this class, especially when we go in to do like a G10 output lines that gather data from the NCI file, sort that data, and then output it. But yeah, I could definitely see at some point in the future another class on how to create and format and manipulate data from a post using Microsoft Excel, because I think that's really a great way to do it. Anyway, okay, buffer number 2. So we're writing 4 consecutive pieces of data, which means that we really need to define 4 variables in order that are in an implied array. So one of the things that I think is kind of a best practice to do is to make sure that your buffer variable names clearly indicate that they are used in a buffer somewhere. Something like B1 or C1 or N1 underscore. Something like this works really well to make sure you're not confusing them with other variables. So what we're going to do here is we're going to say this is B2 underscore, and this is going to be, how about op? And we can make them 0. So this is going to be, how about operation number? And then we want B2. How about TOX? We're going to call this X tool plane. Tool plane origin X, B2, TOY, tool plane origin Y, and then, yep, you guessed it, we're going to do the same thing for Z. Okay, and we're going to start with B2 underscore op, because that is the first variable in our implied array of 4 variables. So every time we read to or write from this buffer, we're going to be reading these values here starting with B2 underscore op. So let's go ahead and save that. And now let's do something with it. So we're going to need some code to write these tool origin values. Now, we could just capture this data and we could output it per operation. But that's not really going to be what we want for normal output. Instead of searching all the way through our program to find the info, it'd be better to get this info in our file header. I mean, that's where we'd really like to see it. So if that's the case, we have to capture this during the pre-read. If we try to just output it during our normal post output, there's no way to look ahead and grab that info and put it in the header, which is why we basically have to capture it and build it up in our buffer during the pre-read and then just output it. Okay, so we've got buffer number 2 arranged. We're going to use B2 for the op number. So let's go look at PWRTT. So PWRTT is really where we want to capture this data. Now we need to be a little bit careful because we need to make sure that we don't go beyond the end of our buffer number. So there is some, let me just save what we've got here. And let's go back and just look at this real quick. So if we look in our generic Fanuc 4x empty lathe post, current record, last record, and it even writes that for 1001, so we should be okay there. We don't need to worry about that. That's for updating the min and max. Okay. Okay, so in PWRTT, we want to either add all of our logic here or make a call to a post block where we set things up. So we're going to have P write buff 2. Now, it doesn't really matter where we stick write buff 2. You notice we just included our language here, our post instructions in the ptool comment post block. But our output is going to come from p header. That's where we're going to actually output this data. So it would kind of make sense to include this near that output. So we'll do it right up here. So we're going to start the P write buff 2 post block. Okay, so we're going to write the information to buffer 2. I'm going to set up a bookmark here. And we're going to go back to our buffer definition section. It's up here. I'll set another bookmark. Okay, and the reason I'm coming back up here is because I need to remember what variables we're using to read and write this from. Okay, so B2 TOX is going to hold our tool plane origin in X. B2 TOY is going to hold the tool plane origin in Y. B2 TOZ is going to hold the tool plane origin in Z. So we could therefore, depending on our, actually, I don't really want this to be operation number. What if we have this as work offset? Okay, we're going to have that be the work offset number. So, B2TOX, B2TOY, B2TOZ, and B2WCS. These are the 4 variables that we need to fill out before we write to our buffer. And what I'm going to do is just make a copy of these. And we're going to paste them in here. And I'm just going to do that to make it easy for me to see what data I still need to address. Okay, So the first thing that we need to do is we need to set some of these values. So B2 WCS equals. Now we're going to set this equal to the work offset number. And if we go down and we look at PWCS, here's our code for outputting that work offset value. The standard kind of notation is that if the work offset value is less than 6, we get the work offset value plus 54. If the work offset value is 6 or greater, we get the work offset minus 5, and we get a G54.1 P1. Now, part of this won't work for us because we cannot combine the string part of the information like that G value and this. So what we're going to do is we're going to record the raw work offset number, and then we'll manipulate it a little later on because we know what that's going to be. Okay, so what we'll do here is we'll just record the work offset. B2 underscore WCS equals work OFS $. Now, we also need to set the value of the tool plane origin for X, Y, and Z. What I'm doing here is a vector equate function. Vector equate copies 3 consecutive variables into 3 other consecutive variables by using the first variable names in the list. So this is going to copy TOX $, TOY $, and TOZ $, into B2 TOX, B2 TOY, and B2 TOZ. So this will set, these 2 lines of code set all 4 of the values that we're going to write. This one line of code here is the equivalent of writing 3 lines of code. So I could do the same thing by doing this. So this line of code does the exact same thing as these 3 lines of code here. It just does it in one line. It copies 3 values to 3 other values. Okay, so in this case, we have captured the 4 values that we want. The only thing that that is a little bit concerning about doing it this way. Actually, you know what? Let's do it this way, and then when we run into problems, we can figure out why. That's actually, I think, a better lesson. So now what we're going to do is say B2 WCS equals WBuff 2, it's buffer number 2, and then we're going to use WC2. We're going to use the correct write counter to write to our buffer number 2. Okay, and we have to start with the first variable in our list to write all 4 values to the correct number. Now, if we go look at PWRTT, one of the things that they do to prevent duplicate output for the tool table is to use this function right here, if tool $ is greater than 0. What that's going to do is make sure that the P tool table only gets called for the first instance of every tool that occurs. Anytime that there's a null tool change, we won't write out that additional buffer logic. So we'll take a look at that in a minute. So we're writing all of our values from PWRTT. Okay. Now we need to actually go and output this data. So we're going to go to pheader. And this is kind of, where we would like our data to come out. So what we're going to do in pheader, first thing we're going to do let's go with an extra line here. Okay, first thing we do is we get the size of the buffer. We read record number 0, which is going to tell us how many records we have in buffer number 2. Okay, so this could be 1, it could be 10, it could be 50. Now what we need to do is we need to output the data from the buffer, making sure that we don't go beyond the size of the buffer. And the way that we end up doing that is with a while loop. So let's go look at our while loop examples. Okay. So determining buffer file size, you read record 0. We've done that. Now, if you're using the while looping command, you can scan through a buffer. So, for example, ploop, okay, post block definition, size equals rbuff, buffer 1, record 0. Get the size. While rc1 is less than or equal to size 1, string data equals rbuff1, rc1, and then we output the string data. Okay, it's this while loop convention right here which allows us to loop through and get our data. So what we're going to do is back in the post, we're going to say while, let's do it on another line, okay, while RC2 is less than or equal to size 2, we're going to continue performing this action. So, what's RC2? RC2 is our read counter for buffer number 2, and it starts with a value of 1. Okay, and that's important because what we're going to do here, while RC2 is less than size 2, we already got size 2 right here, we are going to say that B2 WCS equals RBuff 2, it's the second buffer, RC2. This line right here says I want to load the line of data in buffer number 2, and I want that line of data to be equal to whatever the value of RC2 is. And I'm going to load all 4 of those values into an implied array starting with B2 underscore WCS. So we're reading the data back out of the buffer, and we're reading all 4 pieces of that data. We'll keep in mind that as soon as we complete reading this data, this RC2 gets incremented by 1, so we don't have to worry about doing that ourselves. And what we can do here is we can say, let's output a line number, and let's do S open parenthesis. Before I get too much farther, I still need to format these guys. So let's go back up to our formatting section. Let's paste these in here. Okay, so we've got these values, and I need an FMT we're going to do a G for the G54, and this is going to be an integer. So we'll just make that a 4 there. Okay, this is the tool plane origin in X. We're going to do the tool plane origin in Y. And the tool plane origin in Z. Okay. So what I'm thinking about here is that right now our example is not very well set up to do standard work offsets and extended work offsets. We're going to leave that alone for now. We're going to come back and we're going to do that manipulation a little bit later. For now, we'll just use the standard G value here. So what we're going to do, after we've read the data from the buffer, let's see, we're going to say that we're going to need to output our work offset. So if we look at how we formatted that, we're calling that our B2 WCS. So what we'll do here is we'll say B2 WCS equals B2 WCS plus 54. Okay, and we're going to go back. If we want to do more than 6 work offsets, we could go back in and revise this logic. That'd be pretty easy here. Okay, so now we're going to force out B2 WCS. We're going to force out B2 TOX. Going to do the same thing for TOY. And B2 TOZ. And we're going to do it as a comment, because I think that makes the most sense here. So S open parenthesis, and then how about we do a comment here? We'll do okay, we're going to output the work offset values. Now, in order for this to work for us, what we really want to have is some different work offsets in place here, right? So if I go to our view manager, I'll take top and I'm going to copy it. We got 6 ops, so I'll use 6 times. Okay. So here's our copy of top. I'm going to assign a work offset of 0. Here's this other one. We'll assign a work offset of 1. We'll assign a work offset of 2, 3, 4, and 5. And finally, let's make this 57, 58, and G59. Let's do this again. That should be work offset 0. That should be work offset 1. It's okay. Oh, no. Okay. 5, 4. That one should be a 3. That one should be a 2. And that one should be a 1. Okay. There we go. So we really want this one to be G54. This one is going to be G55. And we'll keep on going down the line. This should be 57. This one's going to be 58, and then 59. Okay. Now, that's all well and good. Except that right now, all of the origins of all these planes are all 0. So let's put in some values here. Okay, so we're just going to assign some values here. Okay, great. So we've got all these things assigned. We've got some code to set those values, and then we've got some code again to write those values back out. So let's see what we get. Okay, so I'll post that out. Oop. Let's see what we didn't do here. Close all that real quick. And let's make sure that this is actually saved. That would be a good start. So I'll repost that. Okay, so we're getting our tool table here, but we're not getting any output from our buffer. So let's debug that. Let's see what's going on. And first off, we can go check that our buffer 2 is actually being written. It is. So let's go open that with Code Expert. Okay, so there's our values. They're actually getting written out, but they're not getting output. Oh, here's something interesting. 3, 4, 5, 6. Why do we have 7 ops? Oh. Okay. So when we're writing that data, here we're writing into buffer number 2. And we're writing it even at the end of the file. So what we really want to do is say if G code does not equal 1003, then we want to go ahead and write the buffer. Okay, that way we don't get an extra or redundant output during the end of file. So if we rerun that, do that. And now let's go back and look at our txt2, and we're no longer getting that 5th output where we don't want it. Okay, so let's go back and look at our output here. See how we're doing on time. We're coming up to taking our next break soon. All right, and then let's go. Okay, so we're writing that definition. So let's do this. I'm going to debug. We're going to look at size 2. And let's also debug RC2. Okay, I want to see what those values are. Okay, so RC2 is 1. Size 2 is 0. Let me make sure I spelled everything correctly. Yeah, I should be reading buffer number 2, record number 0. Okay, let's just try. So read buff 2, record number 0. Shouldn't make any difference. Let's repost. So it's still coming up with a size of 0. It's pretty odd. Shouldn't be doing that. We're writing to buffer number 2. Don't know why it's not giving me the correct size here. So we're going to have to figure that out. Tell you what, we're coming up on a good break time anyway. It's the middle of our class, so what we're going to do is we're going to go ahead and take a 30-minute break, give everybody a chance to get some lunch, stretch your legs, do whatever you need to do. And when we come back, we'll continue digging into this buffer issue, and we'll work out and try and figure out why our buffer isn't working and see what it'll take to get it to work. Okay, so it's like 4:03 now. Let's say okay. So I'll go ahead and see you guys after lunch. Thanks, everybody.